So now we're going to look at something called a stress element. So a stress element is, well, you can imagine you have like something, we'll say a pressure vessel or anything really, a thing, and you have certain stresses being applied to it. You have a couple of normal stresses going in two different directions, like you have someone pulling on it in the x direction with 10 psi's of pressure, and then you have something pulling it up and down with 5 psi's of pressure. So these two are normal stresses, and then you have a shear stress. Someone's applying a shear stress or twisting it so that you get 3 psi's of stress. And so we want to look at how we can manipulate that to get different results, or to find out what the actual maximum stresses are, or different things like that. Because when you write something like this, if you have stresses like this, those aren't that shows you the basics of what types of stresses are being applied, but doesn't tell us everything that we need to know. To illustrate that, I'm going to go back to statics, something you remember from back in the day. If you remember statics, if you have a certain force being applied in this direction, and this is the y and this is the x, if you have a certain force being applied in that direction, what do you do with it so that you can use it better? Well, you break it up into x and y components, right? And so this force can be also demonstrated in two forces, one in the x direction and one in the y direction. And so those are your x and your y components of that one force. And that's the basic idea of what these stress elements are. It shows you what's going on, you get all the information, but it doesn't tell you everything. It's just an x and a y indicator of what the stress is in your element. Just like this is your y and your x components of this force. Neither of those forces is your maximum force. Your maximum force is your resultant force. And so we want to find out how we can manipulate that to find out what our actual maximum stresses are, so we know what our limits are in these stress elements. And so let's do that. So what we're going to do is we're going to show you how to basically rotate the axis. I'm going to redraw this statics picture again I just erased, but like we're going to rotate this x and y axis so that we can get our maximum or get different components for this, or to get our maximum component. So if we wanted to get this resultant force right along one of the x or y axes, we'd rotate the axis so that we'd have an axis that looks like that, and then you had the force running right along your x axis. That way your component force shows you what your maximums are. We're going to do that same thing with this. We're going to rotate this stress element so that we can find out what our maximum stresses actually are. And so one of the ways that we do that is we're given several equations that basically show you how to rotate and find out your new stresses if you were to rotate it so much. And one of those equations is your stress for the x and the y is equal to, well, let's start with the x. Your stress for the x is equal to your stress in the x plus your stress in the y over 2 plus your stress in the x minus your stress in the y over 2 times the cosine of 2 theta plus the shear stress times the sine of 2 theta. So that's how you find, like, if you were to rotate it, there's theta here, these thetas, is how much you want to rotate it. So if you want to take this piece and you want to rotate it that much so that the bottom is along that line, call this theta, we want to rotate it that much so we can find out what the x and y components are in this direction and this direction. So parallel and perpendicular to that line. We use this equation. And so we're rotating it theta degrees, and we're going to plug in our old x and y components and our old shear component, which is 3 psi, and we're going to find out what our new sigma x is. And our sigma y is the same equation, which is why I put a sigma y, except for that you have minuses here and here. So pluses to find sigma x, and use the minuses to find sigma y, and that'll give you your new sigma x and y components. And along that same, to find your shear stress along that same line, we use this equation. Negative xy, or sigma y, x, yeah, negative sigma x minus sigma y over 2 times the sine of 2 theta plus the shear times cosine of 2 theta. And so it's the same thing. For your thetas is how much you're trying to rotate it, and then you plug in your sigma x, sigma y, and your shear right there. And so when you plug that in, you get the different orientation of stresses. Now these are good equations if you want to find out how things work in different directions, but these don't actually, like, you still don't know where the maximum stresses are at. You don't know what your maximum shear stress is, and you don't know what your maximum normal stresses are, your principal stresses. That's what principal stresses are, your maximum normal stress, and in plane is your maximum shear stress. So the equation that we use, well, let's actually talk about this first before we go on to that. Just for a quick example, if we have this stress element and we want to figure out what the new stress are if we rotate the axes 15 degrees. We want to rotate the axis 15 degrees. At least that's what I believe I was using. Yeah, it is. Okay, yeah. So if I want to rotate this 15 degrees, you can imagine this piece rotating so that it looks more like that. $15 degrees isn't a lot. So we want to find out what our new stresses are if you were to rotate it that much. And if we plug these ideas into the equation, and this is 15 degrees, if you were to plug it in, you would find that your sigma x right here is equal to 3.835 is what I got. 3.835